Okay, let's begin our today's seminar, and our today's speaker is Timur Garipov, who will tell us about his joint work with Andrew Wilson, Pavel Zmayov, and mathematics, right, which was recently submitted to ICML.
Thank you for the introduction. So, in this talk, I'm going to present our recent results on Bayesian inference using the trajectory of SGD. But before we proceed to Bayesian inference, let's start with the practical task to which we apply our algorithm, namely uncertainty estimation. So, why do we care about uncertainty estimation? Basically, to avoid expressions like this.
There'll be a long seminar today.
Well, hopefully that won't happen on every slide.
So, we use machine learning models not only to make predictions, but to make decisions based on the predictions we have from our models. And so, before we can make decisions based on our predictions, we want to be sure that our predictions are correct. It means that we not care only about high predictive accuracy, but we would like to estimate some measure of uncertainty, which means to which extent do we believe in our model predictions. So we would like our model to produce some measure of uncertainty, and so basically we want our model to say if it's confident in its predictions or not. And if it's not confident, we can, so if the model is not confident on a given sample, we can not rely on predictions for this sample, and instead of that we can use assessment from people, or process this sample in another way. In deep neural networks, we have we almost always have high predictive accuracy, but deep networks lack representation of uncertainty, and we often provide overconfident or miscalibrated predictions. So there is a lot of work on modeling uncertainty for deep neural networks. So in this work we consider Bayesian approach to uncertainty representation. So Bayesian machine learning provides a principled way to estimate uncertainty. So we define our probabilistic model for deep neural networks. We have a likelihood for observed data and a prior distribution over weights of the neural network. And our goal is to obtain the posterior distribution over the weights of the network. So on the training stage, so the problem is that the true posterior distribution is intractable for deep networks. And on training stage, instead of deriving the true posterior, we would like to obtain some approximation of the posterior distribution. And later on the inference time, we can use this approximation of the posterior distribution to obtain the predictions for new data points. So if you have new data points, we can marginalize our predictive distribution over the weights of neural network, which comes from the true posterior distribution, and approximate this. So this procedure called Bayesian model averaging. And if we use approximate posterior, we can replace in this expectation the true posterior with the approximate posterior, and hope that our approximate distribution will give us good enough predictions. So there are many directions on uncertainty estimation in deep learning. So there are several Bayesian approaches. One of them is Markov chain Monte Carlo, and I recently proposed its stochastic gradient version of Markov chain Monte Carlo. So another approach is variation inference, to fit some variational approximation to the posterior distribution using the variational lower bound. And there are more straightforward and simpler approach called Monte Carlo dropout. So the idea is that in a lot of modern deep neural network architectures we have dropout as a building block. And like in dropout we introduce noise in the weights or in the activations of the network at each iteration of training, but usually on test stage we don't use this noise. Now in the MC dropout it's proposed to also introduce this noise on the test stage and average over different instances of this noise coming from dropout. Yeah, and the last example of Bayesian approaches is called Laplace approximation, which actually uses like Taylor decomposition of the log density of the two posteriors, which you can estimate easily. And with Laplace approximation, we usually fit Gaussian distribution centered at some point, and with the covariance coming from the Hessian of the loss. So, and there is a recent work on introducing Kronecker factored Laplace approximation with the Kronecker factored covariance matrix. Also, there is some work on non-Bayesian approach for uncertainty estimation. One of them is deep ensembles. So, idea in deep ensembles is to just train an independent ensemble of neural networks and average predictions of this network from the ensemble, and obtain better adjusted estimations as we use not only one model but several models obtained from different random initialization. And the last procedure I'd like to mention is that called temperature scaling. So, so it noticed that in deep neural networks, on the last softmax layer, which produce our predictive distribution, we usually have very concentrated probability. So it will be probability which is close to 1 for one class, and over class would have probability close to 0. And in order to avoid that situation, it's been proposed to introduce temperature to the softmax layer, which basically scales the logits, so it's the input of the softmax layer. So in result we obtain some smoothed distribution instead of this discrete distribution we usually have in neural networks. But in order to tune this scaling coefficient, we need to use some new portion of data. Usually we use validation set, but it's not always accessible for us, and we will see it further in the experiment section. Okay, now before we proceed to our method, let's talk about the background. So in our method we use the trajectory of SGD to form our approximate distribution. And so, and what do we know about the distribution of SGD iterates from the literature? There is this work called SGD as approximate Bayesian inference from BayesGroup, and it analyzed the stationary distribution of SGD.
With constant learning rate.
Yeah. With the assumptions I will mention further. So, in this work we consider the following setting. So as usual in SGD, our loss function is represented as an average of n different loss functions, which depends, each of the functions depends on its own object on the training set. So when we have true gradient g of theta, which is takes long to compute, and instead of that we use stochastic gradient which we can obtain easily. So in order to do that, we sample a mini batch from our data set and compute the stochastic gradient over the mini batch. And at each iteration we recompute our parameters theta during the gradient step, but with the stochastic gradient instead of the true gradient. So let's consider the assumptions we use in this paper. So the first assumption is about the gradient noise. So we assume that the gradient noise is Gaussian with some covariance matrix, C of So it gives us following representation for the stochastic gradient. So we know that the expectation of the stochastic gradient is the true gradient, and there's also this noise term which we approximate, which we believe it's close to the Gaussian distribution with its own covariance matrix. So we further assume that this covariance matrix is approximately constant with respect to theta and full rank, so it could be represented in this way. It's basically like Halle's decomposition for this matrix. So given these assumptions, we can rewrite our step of SGD in the following way. And so basically what we have, our difference between the next iterate and the current iterate is just the true gradient multiplied by the learning rate plus this noise component. So for which we take this delta W coming from standard normal distribution multiplied by matrix P, which defines the covariance of the noise. And also we have the scaling coefficient depending on the learning rate and the batch size.
What are the dimensions of the delta W?
It's the same as the dimension of beta. Yeah, so it's like full rank noise, full rank Gaussian distribution. So if we represent SGD, iteration of SGD represented in this form, could be considered as a finite difference approximation of the following stochastic differential equation. So basically we have everything the same here, but in the lower equation at the bottom we have continuous time process instead of discrete time. And our true gradient term is the same, but the noise term now is represented by stochastic process is W of t, which is a Wiener process. And so so I won't go into details of the Wiener processes, but it has the properties that it has independent increments for any given point in time. So if we consider different points of the Wiener process, the difference between them has Gaussian distribution and it does not depend on t.
So this means simply random walk, where each step is made according to the white noise distribution.
Yeah. Also, this process, I believe, defines roll movement.
Mm-hmm.
Yeah, and this differential dw of t is something like a differential of this Wiener process. If we integrate it, we will obtain Wiener process as a result. So now let's add two more assumptions, which will give us a specific form of stochastic differential equation called Ornstein-Uhlenbeck process. So in the assumption 3, we assume that we can approximate this continuous the finite difference equation well with the stochastic differential equation, and we can justify this assumption if our learning rates are small or our gradients are small. Yeah, in our case, the discretization here will become too high, and the dynamics of the finite discrete time process will be different from the dynamics of the continuous time process. And finally, we make assumptions on the structure of the loss in the region of interest. So we assume that the loss is quadratic in some region, which our SGD iterates lie in. It's quadratic with positive semi-definite matrix A. So if we have this assumption, we know the form of the true posterior, as we know is so the loss is just the energy of the posterior distribution. So and if we have this representation for loss, it means that our true posterior distribution is Gaussian with the covariance matrix A.
Well, locally Gaussian.
Yes. So if we substitute all of this into the stochastic differential equation we've seen before, we'll obtain this stochastic process called Ornstein-Uhlenbeck process. And so we good thing about it is that it has analytical stationary distribution, so we know that so we can solve the stochastic differential equation analytically. So if you look at it, so if we ignore the noise term, it basically will have linear ordinary differential equation. And for that we know analytical solution, and this noise term we add happens to be simple enough to allow analytical solution for the stochastic differential equation. So for now we know that the SGD produced.
So, sorry,
Yeah.
the solution of stochastic differential equation is a distribution. It appears so, or not?
It's stochastic process.
Stochastic process indexed by time.
Yeah. And we're interested in this
Process
stationary
indexed by
distribution.
time, but then what does it mean, stationary distribution in this context? First of all, at least for me that's a bit unclear. We started with differential equation, we switched to stochastic differential equation. The solution of differential equation is function. The solution of stochastic differential equation, okay, let it be a random process. But what is stationary distribution then?
Okay, I have following analogy. So if we consider like finite difference SGD, we can consider it as a Markov chain.
Right.
Yeah, and this Markov chain has some stationary distribution if some assumptions hold true.
Right.
So
But
the
then
stochastic
maybe-
process is the continuous time Markov chain in some sense.
Okay. But still, what is the stationary distribution of a random process? Is it a stationary random process?
It's a theta of infinity.
Or is it the result of marginalization with respect to the time? With respect to time?
No, it's a limit of time.
It's a
A limit of infinite time.
Yeah.
Yeah.
If we index random process by time, we get random wave, and if we limit time to infinity, I think it's a stationary distribution we was talking about.
But is it the same that to simply say that we are marginalizing with respect to time?
Time is not random. There is no distribution over, and it's very hard to marginalize over some finite value and get infinity.
Maybe we integrate over time.
So if we go back to like just Markov chain, so to obtain stationary distribution of Markov chain, we find this special kind of agent or vector of the Markov chain matrix.
Mm-hmm.
So yeah, so Markov chain defines linear operator, and so here it should define linear operator over the distribution as well. So if you have continuous time Markov chain, which is stochastic process.
But is it stochastic linear operator or not?
If we operate on distributions no longer stochastic.
No, it's okay. Mm-hmm.
Yeah.
Okay, good.
Yeah.
Now I understand.
I'm not familiar with the formalism enough, but yeah. We are interested only on the results here. And so if you want to take it through, we can. So I can refer to the original paper or some literature on stochastic processes. Okay, so under these assumptions, our Einstein-Uhlenbeck process approximates the dynamics of SGD, and we know the stationary distribution of the stochastic process, so we know approximately the stochastic distribution of SGD iterates. So this distribution is Gaussian, with the covariance defined by the following equation. So here is A is the matrix which we use to define our loss, and B is the matrix responsible for the covariance of the gradients. So from this equation, what we can see is that the covariance is proportional to the learning rate, it's inversely proportional to the batch size, and also inversely proportional to the A matrix. If we scale matrix A by some factor, our covariance matrix we should divide it by the same factor.
So the larger is step size, the larger is variance.
Yeah.
This is reasonable, and the larger is mini batch. The smaller
Is
is variance, and in the limit the variance will be 0,
Yeah.
because there will be no stochasticity. Mm-hmm.
Yeah. So our covariance depends on the learning rate, page size, covariance of the noise gradient in the noise, and our shape of the loss function. So now we know that our stationary distribution is Gaussian, under assumption 4 true posterior is Gaussian, and we can try to tune the parameters of SGD in such a way that we will minimize the KL divergence between the stationary distribution of SGD and the true posterior distribution. So it's just the KL divergence between two Gaussians, and for that we can derive following results: the optimal value of the learning rate. So if we use this learning rate, our SGD will produce distribution which matches true posterior in the best way in terms of the KL divergence.
You mean that then we'll obtain a random walk which locally matches the true posterior distribution?
It will be close to it in terms of the KL divergence. That's all. So I don't say that the KL divergence will be 0.
Well, it will be 0 because our posterior is not Gaussian. It's only locally Gaussian.
Yeah. But we still can. So our
does it mean that our sigma becomes A with the epsilon star or not?
let's see. I don't think so.
I mean, sigma is much more many-dimensional object than the epsilon.
Yeah, we just tune only one parameter, so we can guarantee that you match.
It's more like just scaling.
Okay, so
two covariance matrix.
So this means that by tuning epsilon, we feel the scaling of sigma matrix in such a way, and the epsilon star in such a way of scaling when sigma is more or less of the same scale as A.
The question then is though, what's the point of this epsilon if it depends on B and B depends on A? And if you know A, then you can just construct the whole locally normal distribution and don't care about anything else. You have local approximation of the posterior.
But here we do not have to know B.
Yeah.
Well, the formula.
need to know
Okay, you
trace.
need to know only the trace, but is it any easier to compute?
I think it's easy to estimate.
Yeah, we can try to estimate, but like this are some theoretical results. Yeah. And so there are actually some applications of these results in the original paper, and in some sense we also try to apply this result, but we okay. No, I think let's proceed. So okay, we discussed these assumptions, the results we have. But do you think that these assumptions hold for deep neural networks?
Of course, no.
It's true, and we try to check some of them empirically in order to just to see what happens in practice. So in this experiment we estimate the covariance noise. So on the left plot we just run our SGD and compute the variance of the gradients, and on the plot we have trace of the covariance matrix of the gradients. So these lines which denoted with the label scratch means that we start the process from the random initialization and start collecting covariance from the early stage of training. So you can see that at the early stage our gradient noise is not stationary, at least the trace is not stationary, but there are two more lines denoted as WA, in which we, for these lines, we just trace, we can compute this variance started from the late epoch in training. So we switch to constant learning rate, like epoch 2050, and start to estimate variance starting from this epoch. So, and at the late stage of training, at least the trace of the noise covariance seems stationary. Yeah, but
Is it the same which was denoted as the trace BB transposed on the previous slide?
Yeah.
So this is it.
So we can hope that the covariance of the noise is stationary, but there are more experiments needed to verify that. Here we only consider the trace. And also, if you have the trace, we can estimate the optimal learning rate. And so it's on the right plot. And what you can see, we have some nice values of the learning rate, which is of the factor of 1 million. So to compare with, in practical situations, we use, for deep neural networks, we use learning rates of order like 0.1, 0.01, or something like that. So
And I guess the reason is the large number of D.
Yeah, exactly. So I put the formula here, and so as we can see that we have like batch size and dataset size. It's like something that we have from above, but there are two more parameters: the dimensionality of the space and the variance of the gradients. And so we know that D is very huge. It's like isn't the number of parameters in our model. It's about 100 million. And so we see that we cannot. So SGD don't produce such big covariance, which will lead us to the optimal value of learning rate, which we would like to use in practice. So if we use this learning rate, which we have obtained, our model will just diverge in several iterations. That's all.
So this means that the theorem doesn't hold true for deep neural networks.
I don't know, have you tried it though? Maybe such learning rates are the answer. Theory says so.
Yeah.
But under some assumptions.
Yeah. You're welcome to try, but we haven't tried. But like, if we use 10 or 100, it's also usually diverges. Yeah. So it's actually very interesting, and one possible explanation why this happens could be that actually this SGD may happen in a very tiny subspace, and the effective dimensionality of the SGD traits is not as big as the number of parameters in the model. Yeah, so if we can hope that there is some effective number of parameters which we can substitute in this formula and obtain reasonable learning rates.
So if you use instead of D the intrinsic dimensionality from the Uber papers, what kind of values will you get? Do you get?
Actually, I don't know. We can
Like,
try.
can we try to guesstimate? Would it be the typical 10 to the minus 3 kind of values?
That depends on the relation between the true dimensionality and the intrinsic dimensionality.
Yeah,
Was
sure.
it 1,000 times smaller, 1 million times smaller?
Let's assume that the intrinsic dimensionality is in thousands, 2,000s maybe, 1,000.
Well, then you simply divide epsilon star by 1,000.
Yeah, you see the trace of the covariance matrix is like for ReasNet.
Then there is also S and N.
100.
And so what S and N are the same.
Yeah,
So
yes.
the only thing
okay.
which is changing is D.
So we can try use this intrinsic dimensionality, or we can do inverse procedure. We can estimate like, the optimal learning rate empirically, and then try to estimate the dimensionality of it. So this is a very simple experiment, and we can conduct a lot more experiments to analyze this phenomenon, but it's in a different direction. Okay, and we also have this nice assumption on the loss function, and we assume that it's quadratic with a positive definite matrix. So we computed we wanted to check if the Gaussian of neural networks is close to positive definite or semi-positive definite. But so we evaluated the minimum and the maximal agent values using the Langchus method, and we found that actually we have pretty big negative agent values.
Wait, but isn't the activation function in these networks the piecewise linear reloading, leaky reloading? What kind of activation did you use?
Yeah, it's real.
So,
But then-
does it make sense to even speak about the Gaussian?
So yeah, I need to check the code for the experiment. Maybe we use literal. Yeah, I was not the one.
Well,
No,
the
if you want
reload
to
doesn't
say-
change anything.
This
I
is
mean,
still
if it's
this is the
not
same
if-
function.
It's not with the differential.
Oh, it is differentiable,
Yeah, okay.
except the finite number of points.
Every
But-
piecewise linear function essentially defines a piecewise linear
Oh, okay, I see.
manifold, and its second derivative is
Zero.
zero almost everywhere.
Yeah, that's true.
So you either somehow smooth the landscape before you compute Gaussian. But still it's not clear whether these numbers are informative or not. And whether
Yeah,
we can-
we need to look deeper in what we found here and how we computed these numbers. Oh yeah, I will check this.
There is some work that says if we have a sigmoid on the last stage, we can approximate Gaussian
Ah, by the way, sigmoid, yeah.
at the end.
I forgot about sigmoid function.
Okay.
Yeah, that's true.
And you explore the curvature of the loss, which is log-like.
Yeah.
Mm-hmm.
Yeah, we can like add regularizer, like also regularizer, but it wouldn't help with such big negative agent value. So we would have to use very big value of weight decay in order to fix this negative agent values. Okay, so let's proceed to another work we were basing our work on. This is our recent paper about stochastic weight averaging. So in this paper, my co-authors and I proposed a simple procedure which leads to improved generalization ability of deep neural networks. So in the stochastic weight averaging procedure, what we do is we start the procedure from some pre-trained good enough value of the weights. Like on this plot, we just do usual pre-training with decaying learning rate schedule, but stop decaying at some moment. So yeah, when we switch to the constant learning rate schedule and start collecting iterates from SGD trajectory with some frequency. When we average collected models and obtain new point in the weight space called theta SWA. So, and we want to use this point to make at the inference time to make predictions, but before we can do that, we should update the Bayesian statistics because so if our network contains Bayesian normalization layers, there are statistics which we use at the inference time, and here we change the weights of the network and we don't know statistics for this new value of the weight. So on the plot on the right you can see learning rate we used for SWA and conventional SGD training, and the learning curve, basically the test accuracy on the test set. Okay. And you can see that SWA solution leads to better generalization. So in that paper we analyzed why that happens, and we connect this improved generalization with the observations on loss landscapes. So here we took ResNet on CFR 100, and so we have on the plot we have 3 points in the weight space. One is denoted as epoch 125. It's our pre-trained model. And starting from this pre-trained model, we run two procedures: conventional SGD and our stochastic weight averaging procedures. So we have these 3 points in the weight space, and we consider a plane which contains all of these 3 points and draw cross sections of the loss landscape and test error landscape in this plane. So, as expected, SGD delivers better train loss, better value of the train loss, but surprisingly, SWA delivers better value of the test error. And so you can on this plot you can see the shift between the train loss surface and the test loss surface. And SWA solution happens to lie in this more wider region, in the center of this white region of the loss landscape. So here's another visualization. It's one D cross section. We interpolate between SGD solution and SWA solution. And basically what we see here is that I already said that SWA lies in the center of this flat region of the loss landscape. Okay, so let's proceed to our method. So what do we know now? That we know something about the trajectory of SGD and its stationary distribution from these theoretical results. And we know that in practice, if we run SGD with constant learning rate and average weights, we obtain point which delivers better generalization performance. So let's push this idea further and obtain not only one point, but try to obtain a distribution over the weights from the trajectory of SGD. So if we want to define, so here we consider the simplest form of the distribution we can use. It's just the diagonal normal distribution in the weight space. So we do actually the same. We do pre-training stage when we switch to constant learning rate schedule and start collect iterates from SGD trajectory. So, and we compute mean of the weights on the trajectory, and we also estimate variance in the second moment, and we use this diagonal normal distribution with the mean in the SWA solution and the diagonal covariance matrix estimated from the trajectory. So, and we can use, so if we believe that SGD approximates the true posterior distribution, at least locally, we can, so basically we fit the Gaussian distribution to the trajectory of SGD and use it. Now we can use it at the prediction time. So in order to do so, we need to draw samples from standard normal distribution multiplied by the square root of the covariance matrix, which is diagonal in the case, so it's really cheap in computational time, and at when we add the mean point, which is SWA solution. So we can think of more complicated distribution. So if we don't want to use diagonal approximation, we want to use low rank approximation. And in order to do so, we propose to collect last k samples from the trajectory of SGD, estimate the deviation matrix, which is basically for each sample from the trajectory, we compute its deviation from the mean vector. So we from this deviation vector, we form a deviation matrix and use this low rank approximation. And so if we want to obtain a full rank distribution, we can combine our low rank covariance with diagonal covariance. So we propose to use a weighted combination with the weights 1/2, which corresponds to basically using the mixture of these two Gaussian distributions. So these two Gaussian distributions have the same mean vector. Yeah. And so averaging their covariance is the same as considering the mixture of these two distribution.
What's the motivation for k minus 1 in the denominator?
It's like unbiased estimate of the sample covariance.
Okay.
Why did you use such kind of running average, but not the SVA solution, SWA?
Yeah, we can try one. So the idea here is that originally we thought that okay, we don't know SWA point in the intermediate point in the training time, so we use this running mean instead of SWA.
But will it converge to SWA?
Yeah, if so, we would
Or you need to
we
also
would
kind of
converge if this running mean is stationary. So if it's stabilized,
Right.
then it's true. But yeah, we need to
Does it?
check that. So yeah, alternatively we can just store these samples, not the deviation, but the samples, and then subtract the SWA point. Yeah. And so to produce samples from this distribution, we do the same. We take our mean vector, which is SWA. We add a diagonal noise, and we add low rank noise, for which we need to sample on the low rank noise from the low rank standard normal distribution. Yeah. Okay, so basically that's the method. It's very simple. The only computational overhead here is storing this. So during training we need to store current SGD iterate, current running mean, and this deviation matrix. So our memory consumption depends on the rank we choose.
Oh, but this is not only during training, during testing as well.
Yeah, during testing.
So you need to keep in memory k rank d by d matrix.
Yeah.
So this means that you need k times d.
K times d parameters. Yeah. So in practice we use rank of 20. So yeah. So we analyzed the connection of this method with the loss landscape derivations. So here we do the following: we take our low rank covariance matrix and do the eigen decomposition for it. So we compute eigen vectors and eigen values, or alternatively you can see it as a singular value decomposition for this deviation matrix D hat, or PCA for the columns of D hat. And in eigen decomposition we have eigenvectors ordered by corresponding eigenvalues, and the more eigenvalue of an eigenvector is, it means that the more variance this eigenvector describes. So the more variance of the trajectory we just can describe with this eigenvector. And here on this plot we draw 1D slices of the loss landscape on the rays along the eigenvectors, and we order eigenvectors by the explained ratio, and we see correlation between the variance explained by a vector and the width of the corresponding direction, the width of the longest loss landscape in the corresponding direction. So we have the widest landscape for the first eigenvector and the sharpest for the last one. And with these dashed lines and circles, we denote the 3 sigma interval of our Gaussian approximation we use. So basically in this low dimensional space, samples from our distribution lie in this 3 sigma region.
How does it mean first and last vector?
So we order them by, the first eigenvector has the largest eigenvalue, and it means that it explains most of the trajectory variance. So the most, yeah.
So we have some physical intuition of this relation between the curvature and the exponent variance. Can you say that they're inversely proportional?
The width and the variance of
The curvature and the variance.
yeah. So
Just like it is in usual Gaussian, right?
yeah.
The larger is variance, the lower is curvature.
At least what we can see from this. Yeah.
So this means that in some sense we can treat well the set of samples we collect as a set of samples from a Gaussian distribution, whose covariance matrix is given by the corresponding curvature.
Yeah.
Nice.
So yeah, it actually means that our covariance matrix we obtain in our method is well described the covariance of the loss levels. We can see it further on this visualization. So here we have not one D-slice, but two D-slices in the planes painted by top eigenvectors. So the leftmost plot is spanned by first and second eigenvectors, and the rightmost plot is for the planes painted by third and fourth. Yeah. So here again we can see that the loss is wider for the top vectors, but also what's really surprising that we can see any correlations in the loss levels sets in these planes.
Correlations with what?
So this loss levels are let's say ellipsoid form, and these ellipsoids are aligned with the axis of the plot. It means that so it's not only about the curvature but about the before
about the orientation. Yeah. One question: do you understand the intuition behind these Lissajous curves in the trajectory? Did the prof tell you what was the explanation?
No. I know,
So for
I know
you,
about
this is just mystery.
No, I know about this paper, but I don't know about it.
And we don't know the explanation
Okay, and
of why it behaves in such a way.
And what it is?
I'll tell you afterwards. After this thing there. Unfortunately, there's nothing strange and nothing surprising and nothing useful. So this is just some kind of artifact.
Okay. Yeah. So we were talking about these projections of the trajectory, which are denoted by these pink lines, and so we have some pretty fancy shape. And there is a paper which shows that it's actually Lissajous curves, which can be derived from stochastic processes. Okay, so with these results, we argued that our approximation to posterior, describes the geometry of the loss well in this low-dimensional subspace of the SGD trajectory. Yeah, and it also means that we describe the geometry of the posterior in this subspace also well, because the loss is just the energy of the posterior distribution. Okay, so before we proceed to the experimental results, let's again take some notes on patch normalization. So if in our network we use patch normalization, we need to, so how does the patch normalization work? On training, we compute this mu and sigma statistics from the mini batch coming from the data set, but on the test time we don't have mini batch, and we want to use the statistics. We still may want to use the statistics, and in order to do so, conventionally we use some statistics mu-tuned and sigma-tuned approximated from the training data. So usually we just use running mean of this mu and sigma from the training stage. there's the problem if we want to change the weights of our network. For example, it happens when we sample weights from our distribution. We obtain some new weight vector which we haven't seen before, and we need new of the statistics for it. So yeah, the simplest thing we can do in this situation is just to fix these new weights and do a forward pass on the training set or on the part of the training set and estimate the statistics from that forward pass. So in practice, for experiments on CIFAR dataset, we do a pass on for each sample from our approximation, we do a pass on the full training dataset, and for our experiments on ImageNet, we do a forward pass on the 10% of the training dataset.
In order to restore this Bayesian statistics?
Yeah.
But we won't make the procedure totally inefficient. The procedure of further averaging. So if each time we need to pre-compute those statistics.
Yeah. Actually, we have pretty good results that shows that we don't need to use the full training dataset. We can use a very small portion of it.
Mm-hmm.
Yeah. But it's still the problem, and like it's a common problem for all Bayesian methods which deals with the networks which have Bayesian normalization. So in Bayesian neural networks, we have to sample. We always sample the weights, and we have to do something about the Bayesian normalization statistics.
Probably the best way is just to get rid of Bayesian normalization.
Yeah, that's a good.
Hopefully one day we can add that as well. Yeah. So let's proceed to empirical results, and so let's discuss how we measure uncertainty in our experiments. So there are actually several ways to do that. The first way is to compute the negative log likelihood of our predictions on the test set. So negative log likelihood is different from the accuracy. So in accuracy, we only care about whether we predict the true label or not. But if we use negative log likelihood, we care also about which probability was assigned to the true class, and if we assign high probability to a wrong class, we will be penalized very hard by negative log likelihood.
But don't you in practice have not access to the right answer? Like, why are you watching on the likelihood of the true answer, whereas in practical applications, when you would like to measure uncertainty, you would not have access to this information?
Yeah, that's true. It's depends on what we want to measure. So yeah, negative log likelihood doesn't tell us everything about uncertainty of our model. It just tells us that so if we have data with true labels on which we can evaluate negative log likelihood, and it's small, we know that we don't make overconfident errors. So we either predict true label or we predict wrong label, but with not very low probability.
Okay.
Yeah. Well, yeah, calibration is another measure of the uncertainty, which is closer to what was mentioned, so this problem. So in calibration, we consider relation between the confidence of our model's prediction and the accuracy of the prediction. So we define confidence for a neural network as the maximal probability in the softmax output. So if we have, like, we predict some label with a probability 0.6, it means that we're confident. Like our model believes that if probability 0.6, it will be the right answer. And so we want, and we want actually to have in practice this probability equal to 0.6. So here we consider the probability, so the accuracy for the data points with given confidence. So, yeah. So
in other words, we expect that among all objects which we classify with to some class of the probability 0.6,
yeah.
we expect to see 60% of the objects which were classified in the right way, and 40% of the objects which were classified in the wrong way.
Yeah, exactly.
The same situation with the 0.7, 0.9, 0.2, and so on.
Yeah. So we want our model if it's confident, if like probability, so it has confidence p. We want the accuracy for these data points to be equal p.
So it's important to realize that this is orthogonal requirement to the classification accuracy. So we may have a model which estimates uncertainty very accurately, but the model itself is completely inaccurate, and vice versa.
That's true. Yeah, and if you want a scalar measure of calibration, we can estimate the called expected calibration error. So we basically over all points. So we evaluate the confidence of our model predictions for each data point in the testing set, and when we group our points based on their confidence of the predictions, and we in this group we estimate the accuracy, we compute the accuracy of the predictions for this group, and compute the difference between the confidence and the accuracy. Yeah.
I have a question. When you tune the temperature in your softmax layer, do you actually like watching on this metric? Because like a standard way is to like just maximize the likelihood with respect to the temperature.
Yeah, in temperature scaling, we optimize negative log likelihood. So
Yeah.
with respect to temperature.
And actually, for what purpose you need this like expected calibration error? Just to like, why not use just negative log likelihood? It's like,
But it's like it's another measure.
yeah, it's another measure, but is it even informative? Because you cannot like achieve a perfect calibration in any sense with neural networks or any meaningful model. So like computing these quantities would be not obviously better than measuring the negative log likelihood of a model. Or it's just like another measure to compare of which is like sensible enough.
Yeah, I think it's
Too many legs, anxious.
the former there. But like, what's the problem with expected calibration? So it's tells about like different aspect of uncertainty.
I'm not sure if it's like a different aspect.
But
it's like
Why? But, it's different metric, and both
yeah, it's
metrics are
different
quite
metric,
reasonable.
yes,
But
but
if it's like if we have two models and for the like one model calibration error is lower than for our, that
yeah,
means
just
that
like
it's more calibrated and we can believe in the confidence that it produces on its prediction.
yeah, okay. I'm just saying that in practice, everybody do good likelihood
But
for achieving the calibration.
isn't the NLL also forces some classification consistency? Like it does not let the model deviate from good predictions. Whereas here, I guess the perfect model for the calibration would be a random guess. And here, optimizing this objective to the extreme, you would guess, you would get a random guess. I mean, if your model could make random guesses, of course.
Well, in some sense, if you have like high temperature, you
So yeah,
would have a random guess out of the box.
yeah.
Because the
So,
temperature is high.
this loss is like more permissive in the sense it does not penalize your model for losses in accuracy.
Okay, fair point.
So so these two metrics were about measuring uncertainty on the like testing set, which is we assume to be from the same data distribution, and another property people usually want from uncertainty estimation is that if we give the model a point out of the training distribution, we would want our model to signalize, like to give us a signal that it's like something different from the model, what model is trained on, and we don't know what to do with the point. But it's like in some sense something like orthogonal what we do in training, because it's more about like detecting outliers and like modeling data distribution. But if and we during training our models, we do not force it to have this property in any way. At least we use some adversarial training or something like that. But we still can have some nice results on this out of sample points as a side effect if we use Bayesian approach or any other approach.
By the way, have you tried to perform adversarial attacks? Such kind of ensemble estimation. It would be interesting to see whether it became more robust or it's catastrophically unrobust like all previous models.
Yeah, we can try. Yeah. Yeah, but we haven't tried in this area. Not for now.
Okay.
And there is another measure I haven't mentioned on the slide. It's the accuracy of the predictions. So we can. It's a bit orthogonal to the uncertainty and the accuracy. We can be very uncertain but inaccurate, and so we want to have both, high accuracy and high uncertainty. And it's a good thing about our method that so it has accuracy similar to that of SWA. So the accuracy for SWA is very close to SWA. It's sometimes better. For most of the time, SWA is better. Yeah, and for other methods like SGD, KFAC Laplace, dropout and temperature scaling, so we have lower or the same value. For temperature scaling, temperature scaling doesn't change the accuracy because it doesn't change the prediction of the model. Yeah. So yeah, there's an interesting thing about dropout because actually there are many ways in which we can apply dropout to this, combine dropout with these methods. So we can apply dropout to SGD solution or to SWA solution, or we can go in even further and combine dropout with SWA. Sample weights from the Gaussian distribution and then sample dropout masks and use that for averaging. And here we report results for dropout with SWA. Yeah, and we have some rows missing for dropout because we cannot make it to work on some architectures like ResNets are known to not work well with dropout. And actually the problem is that it's not clear how to apply dropout to this ResNet because we don't use it by default. And there are a lot of parameters we need to tune, like at which layers we want to place dropout with which and with which parameter P we want to use.
Dropout, yes.
Yeah, dropout.
In SWA dropout, was the network trained with dropout or just validated?
It was trained with dropout. Yeah. So for datasets we have CIFAR 10, CIFAR 100, ImageNet. So on ImageNet we start all the methods from the pre-trained point. So we have pre-trained points downloaded from Torch Vision, and we run our. So it's we report the accuracy of the pre-trained models in SGD column, and for SWA and other methods we do pre-training. We do training for 10 epochs starting from the pre-trained model. And the last 3 rows corresponds to the experiment in which we do a kind of transfer learning task. We train our model on CIFAR 10 and then evaluate it on STL 10, which has different distribution of images but for pretty the same classes. So this dataset has 9 classes in common. So we can consider it as a simple transfer learning task. Yeah. So we have results for accuracy. Now let's proceed to the negative log likelihood. So here for the same datasets and methods, we report negative log likelihood on the test set in this graph. So the x-axis on each plot doesn't correspond to anything. We just use it to separate these points horizontally. And on the y-axis we have negative log likelihood, and the lower value we have, the better it is. So SWAG and SWAG diagonal are consistently among the top 2 methods, and we work especially well on ImageNet and this transfer learning task. And the closest competitor to them is temperature scaling, but compared to temperature scaling, we don't use any validation set, which is not always available, which we can see for STL where the temperature scaling failed, because we can tune the temperature on the, so here we tune the temperature of the samples from CIFAR10, not from samples from STL10. So here are the same results in the table. So these results were obtained by averaging among over 3 runs of each method from different initializations. I removed the deviation values to fit the table in the slide. You can find the deviations in the paper. So on this slide we report calibration plots. So here it's a kind of calibration diagram. On the x-axis we have the confidence of the model for our objects, and on the y-axis we have the difference between the confidence and accuracy. So if we above 0, it means that we produce overconfident predictions, and if we below 0, it means that we underconfident. So the ideally calibrated model is denoted with this black dashed line. Yeah, and here again we can see that SPEC and is among the top 2 models, and again closest competitor is the SWA with temperature scaling, but it fails on to provide calibrated results on transfer learning.
Timur, I would also plot the upper bound, the maximum possible upper deviation from the dotted line.
Yeah, but
because for example here you just can't go upper than this. So there's some bounding curve.
yeah, it's true. Yeah, usually people use on x-axis confidence and accuracy on y-axis, but I find it easier to estimate the difference from the horizontal line rather than from diagonal.
Yes, but again,
Yeah, we have
these plots are a bit counterintuitive, and we need to understand, to realize that they're upper bounded. And it's interesting to see
how close we are.
yeah.
How, it means how bad we are.
Exactly.
It's true. And also we use this distorted scale on the x-axis. So it's not uniform scale. And the reason for that is that for all points we have very confident predictions produced by neural networks. So most of the predictions are close to 0.99 something. So it's and so we have this scale which can make our points on this plot not so dense. So we can see difference between that. Yeah. Here again results summed up in the table. Yeah, and the last experiment is this out of sample image detection. So for this experiment we train our models on 5 classes of CIFAR dataset, and we will compute their entropy of the predictions on the over 5 classes, which we didn't see during the training. So if we use this out of sample data, we want our model to produce unconfident predictions for that. And so what we want here is actually to obtain a predicted distribution closer to uniform. So and we hope that the bigger value of entropy corresponds to we can use it as a signal that we have something strange in our data. Don't want to process this point. So we here have qualitative results, the histograms of the entropy for why there's net on this data set. And also we compute the discretized and symmetrized chiral divergence between the distribution of the entropies for in-class and out-of-class data. So it basically, this chiral divergence says how far is the blue distribution from the red one. So our baseline is SGD. Do you see that SWA has bigger values and temperature scaling doesn't help that much with this measure. Yeah, basically that's all of my talk. So to conclude, let's sum up by saying that so we can use SGD trajectory to perform approximate Bayesian inference, and actually there are a lot of useful information contained in the SGD trajectory. And it's very interesting that there are prior works that suggest that the SGD trajectory lies in the low tiny space, subspace of the weight space, and it's an interesting direction for the future work to try to analyze the posterior distribution in this low-dimensional subspace.
One amendment. Previous works you put that GD trajectories lie at 10-dimensional point, not SGD. Okay, any questions?
Do you have experiments with small networks and small data sets? Are there any effects there?
Yeah, we tried to run experiments for neural network regression, where people usually use quite small networks, and we cannot obtain some positive results there, even for SWA. Even the weight averaging doesn't work.
But doesn't work.
Do you mean what?
Yes.
We just do regression on some small data set like UCI with some small network, two-layer perceptron.
And?
And we do conventional SGD training, and we do stochastic weight averaging, and it doesn't seem to help.
Oh, this means the results are the same or worse than SGD?
It's the same.
The same.
That is what we should expect in this situation.
Yeah, and we believe that the one source of the problem could be overparameterization, because in regression we have pretty small networks, and the situation, the properties of the loss and this structure of the weight space is different compared to image classification task where we use highly overparameterized networks.
And
It's only one.
what is the amount of data in these small programs?
So it varies from hundreds to 10,000. UCI.
And what is the number of parameters in your small deep neural network?
It's usually 10,000 or 100,000.
But this means that they're still overparameterized.
Yeah, but
They're still overparameterized.
yeah, that's true. But here we have 50,000 data points and
So here they're overparameterized by a large part.
yeah,
Mm-hmm.
the extent of the overparameterization is different.
Okay. So any more questions? If not, then let us thank the speaker for very interesting talk.